Okay. Are there any questions from the last class? No? Everything's clear? Okay. All right. Then we continue. Okay. So we've seen or we've discussed till the addition of subspaces. What screen? Oh, yes, yes, you're right. Yes, sorry. I don't think there is anybody online, but anyway. Yeah, so we've discussed till sum of subspaces. Okay, now we'll move on to a slightly different topic. Okay, on what is called the inner product or the standard inner product. Okay, we discussed two types of operations on vectors, right? What are the two types of operations? Scaling and vector addition. We define how to do, at least if you have an n vector, you know how to do scaling and vector addition, right? And I said there is no multiplication operation involved between two vectors, which is not exactly correct. Here we are defining a multiplication operation, which is in fact a generalization of matrix multiplication, as we will discuss in the next module. Okay? And the definition of the standard inner product is this. So I'm going to call it SIP. Okay? The standard inner product is an operation that takes two vectors. Why? Okay, let's assume, and we are defining this in for the Rn space. Okay, you can similarly define for Cn as well. Okay, we'll take two vectors from Rn and it'll produce a single real number, a scalar. Okay, that's the operation. Okay, and the definition operation is essentially this. Okay, and the symbol for this is written like this: that you have one vector raised to the power t, which you know already. It's a transpose operation, but we'll see what is the transpose operation in the next module. For now, just whenever you see a symbol like this, at least for this course, for this module, think of this as a standard inner product, and it's simply defined as the sum of the product of the individual components of your vector, of your two vectors x and y. Okay, you multiply the components that have the same index. The first element of x is multiplied with the first element of y, second with second, so on and so forth, and then you add all those products, and that's the definition of your standard inner product. Okay, you can extend it to complex vectors as well. For example, if x and y were from Cn, not Rn, the definition is slightly different. Okay, so we don't write x transpose y anymore. We write x star y, and you don't just multiply the individual components of your two vectors. You take the complex conjugate of one. Okay, what is a complex conjugate operation? For example, let's say I have a complex number. I'm going to use j instead of I, but yes, j stands for the imaginary number. What is a complex conjugate, which is usually written as x bar? What is a complex conjugate? How do you get the complex conjugate? Well, very simple. You simply negate or change the sign of the imaginary part. That's it. Okay. So that's exactly what you're doing here. Okay. You can maybe just do one example and tell me what the inner products are. What is x transpose y? What is the inner product? How do you compute x transpose y? Not clear? No? Okay, so here, you look at this, right? It's a summation over the n, n numbers, and each of those numbers is simply the product of the individual components of x and y. So, the first number is x1, second number is x2, this is y1, this is y2. The inner product is simply summation over, here n is 2, so I equals 1 to 2, xi, yi. That means you simply substitute the value of I going from 1 to 2. That means this expands to x1, y1 plus x2, y2. Okay, that's simply you multiply x1 with y1, that's 1 times 1 plus x2 times y2, 2 times minus 1. It will be 1 plus minus 2, it will be minus 1. Okay. So this is the inner product of the standard inner product of x and y given by this. Okay. What about this? Instead of vectors, the vectors being from Rn, what if the vectors were from Cn? Or in this case, C2. Essentially, each vector has two complex numbers. This C is the set of all complex numbers. That's the standard notation. So the representation of the standard inner product is like this, x star y. And the definition is, I goes from, here n is 2, 1 to 2, xi bar yi, where you take the complex conjugate of xi multiplied by yi, and then you add it over all the i's. So this will expand to x1 bar y1 plus x2 bar y2. What is x1 bar? What is x1 from there? 1 minus j. What will be x1 bar? Change the sign of the imaginary, it will be 1 plus j. Okay, and then y1 is the same, so it will be minus j. What will be x2 bar? It will be 2 plus 4j. Okay, now you can multiply it and tell me what the answer is. Is that okay? Yeah, that's okay. You can verify that. Hopefully, I have not made any mistakes. Okay. So that's the standard inner product. Okay, another definition that you need to remember. Now, the most general definition of the standard inner product is actually this. Okay, and this is the definition for Rn is a special case of the definition for Cn. Right? For example, if a complex number does not have an imaginary part, what is the complex conjugate of the complex number? If I had a complex number that was 2 plus 0j, no imaginary part, what is the complex conjugate of this? 2 plus 0, 0. Right? That means the number remains the same. That means this complex conjugation operation does nothing to the number. That essentially means you are doing xi yi, not xi bar yi. Right? Okay, so this is the most general expression, and it's good to remember that. Okay? The standard inner product, which means because I said standard, that means there are non-standard inner products as well that you can define. Okay. We look at some properties. You can take the inner product of a vector with itself. So the properties I have listed here are for Rn, not Cn. If it's Cn, there will be slight differences in these properties, but the principle remains the same. If you take the inner product of a vector with itself, the resulting number will always be positive. Okay? Unless your vector x itself is a zero vector. If it is zero vector, then you get 0. Okay? So that's what the first property says. The standard inner product is commutative. So x transpose y equals y transpose x. It's just that if you're dealing with the standard inner product in Cn, this won't hold. Okay, you'll have to take the whole. Okay, but for Rn this is fine. For Rn the standard inner product commutes. And then it's associative and distributive. These are things you can verify. I don't have to go into the details of these. Okay. Okay. That's just the definition. We'll later on look at what the end product actually means geometrically. Okay. The next idea that we look at, concept that we look at, is called the norm, which is essentially the idea of length of a vector. Okay. For example, if I give you two numbers, 5, okay, and I ask you which one of these is larger, you immediately say that 23 is larger. Okay. So on the real line, you have this sense of ordering of numbers, and you can say how far away two numbers are. Or for example, if I give you a point here, and this is the 0, this is the 0 vector of R, I can ask you how far away is this point from the origin or from the 0 vector. Similarly, if I give you another point here, I could ask this. Or you could ask, well, what about R2? There is a 0 vector here. Let's say I have a point here. I can represent this as a vector, as a true vector. Okay. I could ask how far away is this point from the origin. That's essentially the measure of this, the magnitude or the length of the vector. Okay, and that is essentially captured by this idea of norm. Norm essentially means length. Think of it that way. Okay. There are many ways you can define norm. Okay. With real numbers, the norm is very clear. It's simply the absolute value of your real number that tells you how far away you are from the origin. Okay. Turns out as you go to higher dimensions, just in fact, once you go to R2 or more, there are many different ways in which you can define distance. Okay. We know one common way of defining distance in a plane or in R3, okay, which is essentially the Euclidean norm. Okay. This all of us are familiar with. Okay. If you had a vector in R3 or R2, somebody asks you what is the length of that vector, you simply say, well, square each component, add them together, take the square root, that's the length. Okay. From your Pythagoras theorem. Right? That's essentially what is called the Euclidean norm. The generalization of that to a n vector is given here. Okay, you simply take each component, square it, add all of them together, and then take the square root. That's the Euclidean norm. Okay, it just so turns out that the Euclidean norm and the standard inner product are related. Okay, x transpose x is simply summation over I equals 1 to n xi square. And if we simply take the square root of this, that is your Euclidean norm. Okay, so the standard inner product gives you a way of measuring the length of a vector, okay, and that is essentially your Euclidean norm. Okay. But we'll see later that but the idea of the length of a vector is more general. Euclidean norm is just one way of measuring the length of the vector. For example, later on we'll see that there are different ways to say which vector is bigger than the other, or how far away it is from the origin, depending on how you treat the individual components. And for any function which can be called the norm of a vector, you can think of it like this. Norm as a box. Okay, it takes a vector, let's say from Rn for now, and it returns a real number that is always non-negative. It will return a real number that is 0 or positive. It never returns a value that's negative, because negative length does not have any meaning for us. Right? And this, what is inside this box and what output it gives can be quite varied. There are infinite number of functions that can take a vector and give you a non-negative number. Okay? The Euclidean norm here is one example of such. One example of a way in which you can compute the norm of a vector, or length of a vector. Okay? And for any function that takes an input vector and returns a non-negative number, for it to be called the norm of a vector space, for it to be called a valid measure of length of elements in the vector space, it needs to satisfy a few properties. And that's essentially given here. If you say a function, or this box, if you say this box is a valid norm of a vector space, or a valid way of computing length of vectors, then it needs to satisfy the following property. Okay? It needs to be 0 whenever the vector is 0. So to this function, if I input 0, it will always give me 0. That means point 0 has no length. It's got length 0. Okay? It has to be non-negative. What is returned should always be a positive number, or a non-negative number. It can be 0 also. And if you take a vector, it has, say, some length, L. If you scale the vector by beta, the length also should get scaled by the absolute value of beta. Because if beta is a negative number, your norm should still be returning a positive quantity. The length should be essentially beta times, which makes sense. If you say this is the length, and I say now I stretch the vector by 2 times, then the resulting length that you calculate should be 2 times what you started with. Okay. So that's that. And the third one is what is called the triangular inequality. That means we are essentially saying the sum of 2 sides of a triangle is greater than the length of the third side. Okay. Any function that satisfies all these properties is a valid norm. And we'll see examples of other norms. Right? And a common notation that's used for the norm is this double vertical lines. Whenever you see something like this with 2 vertical lines, you have a vector inside. This essentially represents an operation where you're computing the length or size of that vector. Okay. The Euclidean norm is usually written like this, with the subscript 2. Okay, we'll come to what that means later. Okay, we'll look at some examples, and one class of norms are called the p-norms, which is written here. Okay. The formula is fairly simple. If the pth norm of a vector x, and here again, assume for now that these are elements from Rn, they can be from Cn as well. Okay. The pth norm of a vector x, you take the ith component of the vector, take the absolute value or the magnitude, raise it to the power p, add all those elements together, and then take the pth root. Okay. And the pth norm is usually written like this with the subscript p, and p is a non-negative integer. Well, I should not say non-negative integer. Let's just say these are positive integers. We will not look at it. We will not include 0. So P can be 1, 2, 3, all the way, in fact, all the way up to infinity. Okay. When P is 2, then you have the Euclidean norm, which is simply x transpose x square root. Okay. Now, let's go back to R1. And I ask you, okay, let's say I ask you, okay, now if I choose any point, right, and I ask you for the 2 norm, you know how to compute it. You take the vector, you take each element, square, add all of them together, take the square root, and you'll report the number. Now if I ask you, can you tell me the set of all points in R2 that have a Euclidean norm 1? Okay. Those must be some points here, right? In fact, there will be infinite number of points that have norm 1. What would those look like? If I were to indicate those points on this plane, right? Why would it be a circle? Yes. So that's because what is the Euclidean norm? Euclidean norm is simply x1 square plus x2 square equals 1. I'm asking what are all the points x1 and x2 in R2 which have Euclidean norm 1. Say any vector that satisfies any vector x1 x2 that satisfies this equation should be a vector with Euclidean norm 1, right? Now if I take the square root to the other side, this is equivalent saying x1 square plus x2 square equals 1. It is nothing but the equation of a circle. Right? That means the set of all points with Euclidean norm 1, okay, are essentially points which essentially form a circle of radius 1. That's important. And the radius is the Euclidean norm of all these vectors. What about set of all points with Euclidean norm 2? Right, same, it's just that it's a bigger circle now. Okay? Alright. That's essentially what I've shown here. The red circle is essentially set of all points which have constant Euclidean norm. I don't know what the norm is here, but they all we know is they all have the same norm. If you compute the Euclidean norm of any point on the circle, they will all have the same value. Okay. But there are other norms as well, as I said. P can be any value from 1 to infinity. Okay. If the value P is 1, okay, what is the expression for the Euclidean norm? So, sorry, not the Euclidean norm. What is the, if the value P is 1, what is the expression for the 1 norm, P norm? Well, you go back to this expression, you simply substitute for the value of P. P is 1. So that means the 1 norm is simply summation over I n P is 1, so you're not raising it to any power. 1 by P is 1, so you're not taking any root. Okay? Essentially, this says the 1 norm, or another way to measure the length of a vector in Rn is you simply take the individual elements, take the absolute value, and add all of them together. So, a vector which has relatively large values for its components would essentially report a larger length, or it would be at a larger distance than something that's got smaller values for its components, which makes intuitive sense, right? Okay, so that's all fine. Algebraically, that's okay. Then you could ask, well, if the set of all points with the constant Euclidean norm look like a circle, you could ask, what do the set of all points with 1 norm equal to 1 or a constant 1 norm look like? Okay. It turns out, I won't explain how this is. It turns out it will look like this. It will essentially be a diamond. Okay, you can verify this later on. Okay. Because in each of the quadrants, you essentially have x1 plus x2 or modulus of x1 plus x2. That essentially results in 4 different lines in the 4 quadrants of R2. Okay. So that's for 1. Okay? And the 2 norm is very common. The 1 norm is also quite common. And then another norm that is quite common is the infinity norm. Now, if you go by the definition, right, you should ask, well, that makes no sense. That means we have an expression like this. Power infinity. We have no idea how to compute that. Anything raised to the power infinity should be infinity, right? So, of course, this is not how you compute it. Okay? Whenever you have infinity involved, you don't actually substitute infinity. You ask, okay, as the value of p becomes larger and larger and larger, as it tends towards infinity, what does my quantity tend towards? Okay? It turns out that the infinity norm is actually this maximum over I, okay, all the different individual elements. You essentially take your vector, you take the absolute value of all the components. All of them will be non-negative numbers. And then you ask, what is the largest value among those n components? And you simply report that as the length of your vector. Okay? And it is also easy to show why this is actually the most natural definition for the infinity norm. It just comes out that way. Okay? So those are 3 commonly used norms. So the 2 norm, the 1 norm, the infinity norm. Okay. We can similarly ask a question like we did the last 2 norms. What is the geometry of a set of all vectors that have a constant infinity norm? Okay. It turns out that it will essentially look like this. It will be a square. Okay. These are all points with the same infinity. Okay. So, 1 norm was like this, 2 norm was like this, and the infinity norm is like this. Turns out any value between 2 and infinity will have a norm that looks like this. Essentially, you started with a diamond, it became a circle, and then as you increase the value of p, the circle slowly gets deformed into a cube, so it kind of looks like this. You can verify this by writing a program and computing this as well, but that's what will come out. Before we move on, we'll simply compute the norms of some vectors so that you're comfortable with how to do this. Okay? Let's do R2. What is the 1 norm of this? And then you can tell me what is the 2 norm. And then let's do the 4th norm. What is the 1 norm? Okay, 1 norm. Look at what they go back to the definition and compute it from there. When p is 1. Yes, 2 plus 1. That's 3. Okay. What about 2? Three. Square root of x1 square plus x2 square, right? Yes. Okay. What about the infinity norm? 2. What is the vector that's like this? No, here. you always have to take the absolute value. So it will still be 2. Okay. So it's 2. What about the fourth norm? You might have to use a calculator for this if you have it on your phone. But yeah, but you can tell me what the initial expression is. This will be the fourth root of 2 power 4 plus minus 1 power 4. That will be the fourth root of 17. Okay. You don't have to compute. That's the fourth norm. Okay. As I said, these three are very common. They have lots of applications. The other peak norms, maybe not that much. Maybe there are specific exotic cases where they are useful, but they are not as common. See, I noticed that if from the way we defined, so now we have a way of measuring length of vectors with respect to the origin. That means if you have two vectors, x1 and x2, we can also find the distance between them, right? By simply taking the difference between them and computing some peak. That will tell you how far away the two vectors are from each other. Okay. When x2 is 0 or x1 is 0, that's a special case where you're only looking at the length of the vector from the 0 vector. If you do x1 minus x2, then you are computing the distance of x1 from x2. Or the other way around as well. X2 from x2. Okay. Okay. So now we looked at inner product. We now also looked at how to compute length of vectors. We'll next look at another very important concept called orthogonality, which is essentially the idea of two vectors being perpendicular to each other. Okay, and whenever these two vectors are perpendicular to each other, we often write them like this. X and this inverted T is called the perp symbol. X perp y. That means the vector x is as an angle 90 degrees to the vector y. Okay. And verifying whether two vectors in a vector space are orthogonal in Rn is quite simple. If two vectors are orthogonal to each other in Rn, their inner product has to be 0. It's as simple as that. It means if you multiply the individual components and add all of them together, you should get 0. If you get 0, then for sure they are perpendicular to each other. The extension to Cn would be similar. It's simply that it's the standard inner product in Cn that will be 0. Okay. It's easy to verify this, but maybe this expression, deriving this expression can wait till after we looked at transpose operation and all that. But for now, just simply take this. You can come back to this after we looked at matrix multiplication and transpose operation, and then come and verify that this actually makes sense. Okay? It's essentially a restatement of Pythagoras theorem. If you have a right angle triangle, the sum of the squares of the individual sides will be equal to the hypotenuse, and that's where you get this. And we talked about two vectors being perpendicular to each other, and somehow the inner product propped up. At least the standard inner product propped up. Right? That means this inner product has to have some information, or whatever operation you are doing there must have some information about the angle between the vectors. Okay? And it turns out it is, right? You can use the inner product to actually compute what is the angle between the two vectors. When they are perpendicular, you get 0. If you get a non-zero value, then you can use that value to find out what is the actual angle between the two vectors. Okay. Okay. We know this expression, the definition of the inner product, xi yi. There is another way to compute this, okay, which is you take the 2 norm of x, that's a scalar. You take the 2 norm of y, that's another scalar. Then, where theta is the angle between the vectors. Okay. Well, if that is the case, then we know how to find the angle between the two vectors. You simply move these two to the denominator. So cos theta will be x transpose y divided by the magnitude of x, magnitude of y. And often I might not write 2 here. It should be clear from the context that it's 2. Okay. And theta will simply be cos inverse of this expression. Okay. And whenever this term turns out to be 0, that essentially means that the two are perpendicular to each other because cos 90 is 0. Okay. Now, if this is another expression for the inner product, this also means another important fact, which is often very useful. This means if you take the modulus on this side, take the modulus on the other side, the length of x and y can be anything. Right? I can choose my vectors to be as long as I want. I can choose the components to be 10 billion, 400 trillion, whatever. Right? I have freedom to choose that. But this term here, cos theta, is confined. Right? What is the value of cos theta confined between? Sorry? You'll have to be louder. I still can't hear you. It's always between plus or minus 1. Right? That means if you have two real numbers, a times b, if you take the modulus of that, this will be equal to the modulus of a. You're essentially saying if you multiply 5 by minus 1 and you take the modulus of that, that will be 5, which is equivalent to saying take the modulus of 5, take the modulus of minus 1, and that will still give you 5. Okay. Whenever you multiply, you can take the modulus operation into the individual elements, which means x transpose y, the absolute value will be equal to y cos theta. These two are positive numbers, that means they can come out, they are not going to affect anything. Multiplied by modulus of cos theta. And this value is always less than or equal to 1. It's between 0 and 1. That means this thing here, right, has to be less than or equal to this. Okay, that's essentially this inequality, which is actually a very important and useful inequality. It's usually called Cauchy's inequality, but there are 3 people associated. Cauchy's once, but there are 3 people associated with it. It means the absolute value of the inner product will always be less than or equal to the product of the individual length of the vector. Okay. Okay. All right. Okay. Now we switch again, and then we look at a set of slightly different concepts that are more related to span and linear independence that we discussed earlier. What is linear independence? What is it? It's a property, right? No, it's a property of a set of vectors. Okay? And when you say a set of vectors are linearly independent, okay? No, see again, this is something you should know already. The definition you should definitely know, because if you don't know, then it's going to be trouble going forward. Because our base discussion on bases and stuff relies heavily on linear independence and span. Okay. You say a set of vectors are linearly independent if the only way a linear combination of those vectors can produce a 0 vector is if all the alpha i's are 0. if there is any other non-zero alpha I combination that gives you 0, then the set is linearly independent. Okay? Which is equivalent to saying the set is non-redundant. If there is no redundancy in the set, that means you cannot generate any of those vectors in the set as a linear combination of the other elements in the set. Okay? Okay. Right now, let's go back to a set of vectors xi. Let's assume xi is a vector from Rn. Okay. I have a set. Let's say I have m vectors I equals 1 to m. This simply means this is a shorter way of writing. The set has x1, x2, xm vectors. Now, I have this, right? Now I can take the linear combination of this. When I say I am taking the linear combination, I multiply each of these by some scalar and I add all of them together. And let's say I produce a vector y like that, what I've written here. This. Okay, I've generated a new vector, which is simply the linear combination of the set of vectors xi. Okay. Now I could ask, well, if y equals alpha 1 x1 plus alpha 2 x2, so on and so forth to alpha m xm, I've chosen some specific values for alpha 1 to alpha m. Now I could ask, is that the only set of alpha i's, alpha 1 to alpha m, that will give me y, or is there another set of values for alpha 1 to alpha m that will give me y as well? Right? Or I'm asking, are my alpha i's unique to produce y from xi's, or are there more than one possible way, or there more than one possible way through which I could produce y through the linear combination of my xi's? Okay. It turns out that the answer to the question depends on whether or not the original set that you started with was linearly independent. That means there is no redundancy in the original set. So if this is the original set that I started with, if my original set is linearly independent, okay, and I generate any new vector which is a linear combination of the vectors in that set, this vector y that I generate, I can generate this any vector y using only one possible combination of alpha i's if the set is linearly independent. If the set is linearly dependent, then it turns out that there are infinite number of ways in which I can produce any vector y from the set that I started with. Okay. Now, let's do this. Let's say I start with this. Okay. This is some set. What is the span of this set? Okay. The span is essentially another set, which is the set of all linear combinations of the original set that I started with. That means it is a set that looks like this. 2, 0, minus 1, 0, 0, 0 is also there, 8, 0, so on and so forth. There is only one vector. A linear combination of that vector is simply a scaling of that vector. Okay. So the span will look like this. Okay. Now, if I choose any one of these vectors, let's say I choose this, and I ask, okay, this is my y. How do I produce this vector from my original set x? I'm going to call it capital X. How do I produce this vector y from my original set x? Well, one possible way is you multiply your original vector by, so this will be equal to minus half times 2, 0, and that will produce this. Okay? This is one way to produce it. I could ask, is there another way to produce this? Is there another possible linear combination of this vector which would produce this vector? No, there is no, in this case, there is no other one. That is primarily because the set that you started with, this was a linearly independent set. Okay? Whenever you have a linearly independent set, whatever you can produce as a linear combination using that set can be done in a very unique way. Okay. Now, it applies to everything, not just this special case. If I choose this, the only way I could have produced this is by that's for the case where it's linearly independent. Let's consider another example. Let's see if that holds for it. Is this a linearly dependent or independent set? Independent? How will you verify if it's linearly independent? Well, it turns out it's a linearly dependent set. Okay, that's because I can express this vector as a linear combination of this. Half times the first vector gives me the second vector. 2 times the second vector gives me the first vector. That means there is redundancy here. This is a linearly dependent set. Now I can ask, what is the span of this? Span of this will be set of vectors like this. So 0, 0 will always be there. You can verify why this will be the span. The second element will always be 0. You can verify this by simply going back to what is the definition of span and if this makes sense. Okay. Now let's choose one vector, right? Let's say I choose this. How can I produce minus 3, 0 from the elements of x? Well, I can do this. I can do minus 1 times 2, 0 and then plus minus 1 times 1, 0. That will give me minus 3, 0. Okay. I can ask, is this the only way you can produce it? Is there another way you can produce minus 3, 0 using 2, 0 and 1, 0? Well, yes, you can simply say 0 times 2, 0 plus. This will also produce it. In fact, you can write an infinite number of ways you can produce minus 3, 0 from the original 2 vectors. Okay. So the point I am trying to make is this linear combination is unique, right? Which means the only way I'll get y from my xi's is through a single set of values from alpha 1 to alpha n. Okay, will be unique whenever my xi's form a linearly independent set. If my set of vectors x1 to xi set of xi's is linearly dependent, then there are infinite number of ways in which I can produce any particular vector that can be produced as a linear combination of the original vectors. That's essentially what I'm showing here, the example of where you can produce a vector in R2 in an infinite number of ways because the set that you started with is linearly dependent. For example, let's say we started with x1, x2, x3, which are the 3 vectors which I've drawn here, x1, x2, x3. This is a linearly dependent set x1 to x3 because x3 can be written as a linear combination of x1 and x2. Okay. Now, let's say I want to produce this red colored vector, dashed red vector. It turns out there are an infinite number of ways you can stretch and compress the 3 vectors and add all of them together to produce your minus 2x1. Okay. If there were only two of them, right? Let's say x3 was not there, then there is only one way in which you can produce any vector that you get from R2. Okay. Okay. Now, the reason that idea is important is because that brings us to a very important concept in vector spaces, which is the idea of a basis. Whenever somebody says a basis, they're talking about a set of vectors. Okay. And for a set of vectors from a vector space to be a basis for that vector, the set has to satisfy two properties. It has to be linearly independent. Okay. And two, it must span so that's essentially a fancy way of saying, if you say for us to call a set of vectors as a basis for a vector space, that set has to be non-redundant. That means there should be no redundant information in that set. And I should be able to produce every element in my original vector space as a linear combination of this set that I have. Okay? And that's any set that satisfies these two properties is called a basis. Okay? A basis essentially means you can use that to generate any element in the vector space that you want. Okay? For example, we're talking about the real line. Okay? Let's say I have a set. This is a set. R is a vector space. I'm going to call this set X. I could ask, is this set a basis for R? Okay. Whenever they say that, it simply means, is this set linearly independent? Does it produce? Can I use this set to produce every element in my original vector space? Is this linearly independent? Okay. It is. Because the only way you can produce a zero vector using 1 is if you multiply 1 by 0. There is no other way you can produce 0, so it's linearly independent. Okay? So the first criteria is satisfied. The next one is, it says it spans the entire vector space. That simply means, can I produce every possible real number using just this one element in this vector? I can. I simply take that, multiply it by a real number, I'll produce any real number I want. I mean, it spans R. Okay. Because it satisfies both of them, you can say X is a basis for R. Okay, I'm going to stop here for today. We'll take this up again from Monday. If today's classes are not more difficult than the previous one, you should go back and think why I keep saying you need to know the definitions. It's going to be like this for quite some time. Things are going to build on top of the other ideas. So if you're not comfortable with that, it's going to be very difficult to make sense of any of these. Then again, these are relatively simple ideas. It's just that you need to know the definitions by heart. So by Monday, I hope, if I ask you what is linear independence, even if you don't understand it, you should be able to give me the definition blindly. Okay. And then when somebody asks you, is this linearly independent, you simply go back to the criteria and just verify it. You apply the definition. There is nothing more to it initially. Okay, alright. Are there any questions? Okay, alright. Then we continue this on Monday. Thank you.